It's my pleasure to introduce Manuel Endres as our virtual AMO seminar speaker for today. Manuel did his PhD at the LMU Munich and the Max Planck Institute of Quantum Optics, and there he built one of the world's first quantum gas microscopes and applied it to doing groundbreaking experiments on many-body physics of ultra-cold atoms in optical lattices. He then moved on to Harvard for his postdoctoral work, and there he pioneered methods of scalably assembling ordered arrays of single atoms, which he has continued to be advancing since joining the faculty at Caltech. There he's been doing really beautiful experiments applying optical tweezer arrays towards precision measurement and quantum information processing, and you'll be hearing more about that today. I'll just mention that he's been recognized with numerous awards, including the Air Force Office of Scientific Research Young Investigator Award and the NSF Career Award. And before I hand this over to Manuel, I'll just remind those of you, remind our regular participants and tell anyone who's new that if you'd like to ask questions, you can either enter them in the Q&A here in Zoom, or if you're watching via ZooTube, you can type them into the chat there. Manuel will pause a couple times during his seminar, I hope, to allow us to read your questions. And you should feel free to enter those questions before he pauses at any time, and we'll ask them at an appropriate point. We particularly always encourage questions from our students and postdocs. And if we don't get to your question during the seminar, we will have an open discussion with Manuel after the seminar. And there'll be a link posted to that in the Zoom chat and in YouTube at the end. So with that, I will hand it over to Manuel to tell us about quantum science with tweezer arrays.
Thank you, Monica. And first, thanks to the organizers for pulling together this wonderful series. I think this has been really nice for everyone during this kind of really difficult time. Otherwise, and also thanks for giving me the chance to present some of my results. So I'll be talking about like a past years of trying to use tweezer arrays to control individual neutral atoms and to use these systems for various applications in quantum science. I'll start very broadly. I mean, what we're doing is situated in experimental quantum science, and there's many different systems that people use, ranging from traditional solid-state materials to photonic systems, solid-state qubits. And what we're using is neutral atoms, which is basically like standard AMO in a sense. I always find it fascinating that you can have like such a variety of different experimental approaches, but at the same time, we kind of have a common set of goals mostly. And I'll briefly list these, and I'll come back to this various times over the talk. I mean, many of us are interested in quantum computing. I'm particularly interested in quantum simulation and studying many-body physics. Of course, the mainstay of AMO has always been precision physics. And we're now at a stage where we're really all interested in maybe seeing advantages from using entanglement for precision physics, which is sometimes called quantum metrology. And in the end, we all want to connect things up to quantum networks, to really connect quantum computers or connect quantum sensors. So these are, roughly speaking, the goals. Maybe not everyone agrees, but I think most of us would say these are common goals in the field. And this is all good, but there's a series of experimental challenges to reach these goals, and I'll highlight two sets of challenges here. One is a kind of engineering challenge, which is some sort of the competition of scaling up and remaining a control. So we want large homogeneous systems to do these things, and at the same time really want to have a control over individual constituencies and their interactions. So this is, of course, some sort of competition, and it is hard, and we all sometimes basically are fighting this kind of competition. At the same time, I think there's a physical challenge, which is the following. And if you want to run a quantum evolution, the probability of no error is typically exponentially small in system size. So if you have some sort of a single atom, a single spin error rate gamma, your probability for no error would basically decay with an exponential function. But if you have multiple atoms, it's the product of all probabilities. So this scales basically exponential in n. At the same time, for most of the applications, we need to build up a substantial entanglement. And if the interactions are somewhat local, entanglement only splits linearly in the system. So if you want to build up entanglement over the full system size, this would typically take you a time scale that is as long as your system is long, basically. This is what I call linear size. So in 1D, this would be the length of the chain. In 2D, this would be the number of particles to the power of 1/2. So, and these things, they kind of hit you twice. And then you can also take this time, for example, and plug it up here. So you could say, okay, what's the probability of no error to build up substantial entanglement? And it would scale like this. It would scale exponentially, but not just with n, but with a higher power of n. And that's actually quite hard. I mean, unless you don't have error correction, which is even harder, this is what you're running into if you do some sort of a quantum evolution on a system that's local interactions. And I'll come back to this numerous times, and in particular in the very end, where we actually see this kind of competition now in data. The talk more broadly is about how we can address some of these challenges with individually controlled neutral atoms, and in particular now using alkaline earth atoms. Okay? So here's a brief outline. I'll talk about optical tweezer arrays and how we basically assemble compact and defect-free arrays. I'll give a brief introduction to this to set the stage. I'll then talk about Rootback interactions, and in particular about their limits. And we use Rootback interactions to entangle atoms in these arrays. And then I will give some sort of a walkthrough of some of the most recent results at Caltech using alkaline earth atoms concerning narrow line cooling and high fidelity imaging. I'll talk a little bit longer about our new single photon Rootback excitation scheme and the results we have been having there. And we'll talk very briefly about a clock state control in alkaline earth atoms. And then I'll give an outlook and show a little bit of preliminary data on quantum simulation that we do now. Okay, so let's go. And before I really jump into the meat of the talk, I'd like to acknowledge the people who really did the work. I mean, I'm just supervising, and they really do everything in their lab. So there's two graduate students, Ivailo and Adam, current and former postdocs, Joni, Jake, and Alex, and we had a visitor from Korea for a while, and Anand, who's an undergrad. We have a collaboration with JPL, in particular, on all the clock stuff, and this helped us a lot. And then, of course, we have theory support, for example, from Hannes Pichler and Mariana Savronova. And I'd also like to thank the Harvard team still, and because I'll show some pictures that are still from my Harvard time, and then all the funding sources. And then we're always looking for new people. So if you find what I'm talking about interesting, you can always contact me. Looking people for master theses, PhDs, postdocs. So we always have some openings for bright and interested people. And I should also highlight Jake is looking for people. He's now an assistant professor at Urbana, and is trying to wrap up his group. And I think this could be a really interesting position for many people. Okay, let me get started. Optical tweezers and atom-by-atom assembly. So what are optical tweezers? Optical tweezers are a very tightly focused laser beam down to a micrometer that you basically generate with a high resolution objective. And then what you do is you stick that tweezer into a magneto-optical trap. And then if you do it right, you utilize what's some sort of a light-assisted collision process. And that process prevents a double loading of the tweezer. So when you later on take an image of what you see in the tweezer, you will see 0 atoms or 1 atom in a tweezer, but never 2 if you do it right. And that has first been observed in this paper down here in Philippe Granger's group already in 2001. And that's a very important process for all I'm talking about. So usually you load the tweezer and either you have 0 atom or 1 atom if you do everything right. Okay, so what we work on is large-scale tweezer arrays now. So there are 2 techniques to generate tweezer arrays. Basically, one are spatial light modulators, which has been used in Antoine's group in Paris very broadly. And there's a second technique that we are using mainly, which is acousto-optical deflectors. And you can also combine both. So I'll briefly explain acousto-optical deflectors and how that works. Acousto-optical deflector is essentially an AOM. So you send in a laser beam and you basically diffract that laser beam with an RF wave that travels through a crystal. And then the diffraction angle is set by the RF frequency. And then if you send multiple RF frequencies into that crystal, you basically get multiple beams out at multiple angles. And with this, you can basically generate an array. And you can control the positioning of each tweezer, and you can switch off tweezers by switching off individual RF comms, basically. Then you can cross AODs and then generate 2D arrays like that. So this is some of the techniques that we're using. So here's a picture actually of 10,000 tweezers. So there's a 100 by 100 array generated with AOD. So these are empty tweezers. This is just a light. So you see that's actually quite scalable in that sense. But of course, this is challenging to fill these tweezers. And this is what I want to talk about now. Okay, so as I said, if you have an array, it's a stochastic loading process from a magneto-optical trap. So you have either 0 or 1 atom in the tweezer. And then if you look at a fluorescence image after loading it from a mod, and you repeat the whole process, you load from a mod and you look at a fluorescence image, you would see a series of images like that. Let me see if this starts. I hope this is visible over Zoom. So every time you essentially see a different pattern, and it's about 50% fit. Okay, so the challenge is to get it to something like this. So you can average these images and it looks nice. What you want is an image like this in a single shot. Okay, so for some applications, maybe not so important, but for others, it is. Say if you want to build a quantum computer or do quantum simulations, you better have a defect-free array every time. So how do we do this in practice? So this builds upon a scheme we developed in 2016, or a little bit earlier than that already, and that we call atom by atom assembly scheme. So we stick a tweezer array into a magneto-optical trap. We look at the occupation with a very high fidelity imaging, ideally. So we identify basically empty traps. We can switch off the empty traps using basically RF frequency control, and then you basically shuffle around traps, again using RF frequency control into a compact array. And this is the idea of this atom by atom assembly. Now here you see pictures of, as a video of before and afterwards. So you see basically a stochastically loaded array and then a compactified array where we moved everything to the left. So this is great, and you can vary the geometry every time. So you can make basically pairs or more complex patterns. And in particular, you can change the geometry really for every shot. So you can basically get a flexible pattern every time you run the experiment if you have enough control on the RF side. Okay. I don't want to say too much about it, as there's multiple groups now doing that. So the original results were from Paris and Harvard and from a postdoc at that time. And there's a group in Korea which has done this early on. Dave Weiss has some really nice results now in optical lattices, and he also was the person who very early on suggested these types of schemes at a time, but probably not many people thought about it. And there's a few other groups doing that now, including ourselves at Caltech. I want to highlight a few features. So you can generate defect-free arrays in 1D, 2D, and quasi 3D, and typically it's around 50 atoms or a little bit more with a reasonable success probability. I'll come back to that in a second. You can change atomic distances to a micrometer to 100 micrometers. You can generate, again, flexible patterns every time you run it. And you have a much faster repetition rate compared to traditional cold atom experiments where you need evaporative cooling. So typically these experiments, they have a repetition rate of a few hundred milliseconds compared to what's normally seconds, 10 seconds, or maybe even minutes in standard cold atom experiments. And this gives you normal opportunities in terms of how you can take data and so on. There's limits to it too. So in particular, there's a number of traps. I mean, I told you I can make a tweezer array with 10,000 traps, but it's hard to generate enough traps that are deep enough to actually trap atoms. So there's some sort of a laser power limitation, how large you can make things. At the same time, if you really want to generate defect-free arrays, the total success probability of that is also a limiting factor. So what you want is a defect-free array is in as many shots as possible. And the probability for that, again, scales exponentially with the single atom success probability. And that includes, say, imaging fidelity and the probability of surviving, say, a move in that arrangement. And it goes with P to the n. So this P has to be very large if you want to scale this up to, say, thousands of atoms. Okay, so these are the limits. At this stage, these are neutral atoms in the tweezers, and there are distances where they basically don't interact. So how can we engineer interaction mechanisms? There's basically different methods. You can do Hubbard-type interactions where you let atoms tunnel, and this is done in various groups. And I think you have seen a talk about that maybe 2 weeks ago. I think these tweezer arrays are more suited to long-range interactions, in particular dipole-dipole interactions based on Rootback atoms. That's what we are mainly working on, or based on molecules, which is a new like a new research trend emerging now. There's like various groups who can now trap molecules in tweezers. Or you can stick these tweezers into cavities and utilize photon-mediated interactions in cavities. Okay, so I will mainly talk about Rootback interactions. Okay, so how does it work and what are the limitations? So if you have a neutral atom in its ground state, typically the electronic wave function is quite small. So now you can excite it to a Rootback level, characterized by very high principal quantum number. Say you go to n equals 70 for some alkali atoms. So your electronic wave function would have a pretty large size, actually. It's kind of 200 nanometers type large. And the main effect of this is that the electronic wave function basically has a very high polarizability, so it can wobble around pretty easily. And because of this, you can have a very high induced dipole-dipole interactions. So this are typically called van der Waals interactions. And these van der Waals interactions, if you really go through the numbers, they scale with n to the 11 with the principal quantum number. So it's a very strong scaling. And they fall off with 1/6 because it's a second order effect. It's not 1/3. Now, if you plug in numbers for typical quantum numbers, you would see that you can have, say, 10 gigahertz type interactions at 2 micrometer distances, and even still a megahertz at 10 micrometers. And this is the reason why this is such a fruitful marriage with tweezer arrays, because at the distances that we can generate with tweezer arrays, we can have very high interactions, and we can tune them by orders of magnitudes by pulling these tweezers apart. So this is really, I think, the true reason why this is so successful, in combination with the fact that decoherence levels are reasonable, and I'll come back to that. Okay. So in a bit more detail, what we do is we compactify an array, and then we shine in a laser beam that excites atoms to Rootback levels. In a very simplified picture, you can write this down as a two-level system where you have a ground state, electronic ground state, and then you excite to say n equals 70, which is a Rootback state, and you like simplify this to a two-level system. And then you basically have a Rabi frequency that's controlled by the laser intensity, and then the tuning that's controlled by the laser frequency. And in a rotating frame, if you ignore interactions for a second, you basically get single atom excitation terms. You get a sigma x term and a sigma c term controlled by Rabi frequency and the tuning. And then if you include interactions, you basically get another interaction term with an interaction matrix Vij. And then one thing to note is that this interaction term only includes a projector on the Rootback state, so it's not really a sigma c term. And the reason is that ground state atoms basically don't interact on any reasonable timescale because they're very weakly interacting at this distance. So it's basically just an interaction that happens once two atoms are in a Rootback state. And again, the cool thing is that you can tune this interaction by basically orders of magnitudes by pulling the tweezer apart to control this interaction matrix here with this 1/6 term. So that's basically the basics of this Rootback array Hamiltonian that you can use for quantum simulation of various types of physics. I'll briefly flash some of this physics. I don't want to go into detail. I'll show some of it in the end again. This would take a little bit too long. So if you just think about the phase diagram in 1D of that Hamiltonian, it's a transverse field, longitudinal field, Ising model with long-range interaction. So there's a very rich phase diagram that consists basically of a disordered phase up here, and then this parameterized by Rabi frequency and the tuning basically. And you can tune things such that you enter ordered phases. These are this famous Rootback crystal. The simplest one is what we call a C2 crystal. That is a Rootback state, ground state, Rootback ground, Rootback ground, Rootback ground in the array. It's basically an antiferromagnetic order that you can reach. And then there's longer range crystals. This is Rootback ground, ground, Rootback ground, ground, and so on. And this, in essence, actually an infinite number of different phases if you really think about it. So this is the ground state physics. Then you have basically non-equilibrium physics on top. So there's various lines where this model is close to integrability. You have quantum phase transitions. Some of them have conformal field theory. Some of them are even more complicated. So it's actually pretty rich already in 1D. And this richness comes from an interplay of quantum effects and basically the long-range interactions that makes it so complicated. And then again, the ground states are kind of known in 1D already. In 2D, it's quite tricky, and the phase diagram is actually not quantitatively known as far as I can tell. And that's something we are exploring theoretically, for example, with Jason Alicea. So we think there might be some pretty non-trivial phases hidden if you tune the geometry correctly. And the non-equilibrium physics is even richer again, so you can study quantum thermalization features, and there's violations of that. You could study conformal field theories, integrability, confinement, all kinds of things are already in this very, very simple looking Hamiltonian. And then if you have a little bit more control in terms of time dependence and maybe local control, it becomes a pretty rich toolbox, not just for quantum simulation, but also for information and metrology, and I'll come back to that. I don't want to show a lot of the old results. I think this would take too long, and I'm listing a few down here. What I want to say is that there has been quite remarkable progress in the past years, partially triggered by tweezer arrays and also triggered by a much better understanding of the coherence rate. And there have been a lot of really cool results, but I think we've only seen the tip of the iceberg in really what we can do with this type of Hamiltonian and this type of physics. And instead of going a little bit at length at this results, I would like to talk about limitations in more detail, because that's really important. So what are actually the limitations of this approach? So a fundamental limitation is the Rootback lifetime. So typically for these states that we use, you have about 100 microseconds if you're lucky, or a bit more. Then in alkali atoms, it's usually not really a two-level system. It's actually, as long as you want to go to an S state, it's a two-photon transition that you have to take. And then you try to adiabatically eliminate an intermediate state. But this basically intermediate state gives you an admixture of that intermediate state in the ground and the Rootback state. And typically that state is very short-lived. That means you get an additional lifetime effect. So you get an effective lifetime that's typically quite a bit shorter than this 100 microseconds. You get additional spontaneous emission from that state. And In addition to that, you have finite temperature in the tweezer, so atoms move around. It gives you a Doppler shift. It's a detuning noise. And even more important than that, you have noise effects from lasers. And there's two types. One is what we call amplitude noise. So this is noise on the Rabi frequency term omega. And the other one is phase noise. That's essentially noise on the detuning term. And these are both extremely important. And it's extremely important to understand them to really make this work. And it's quite non-trivial. It's more non-trivial than we thought many years ago. There's one more time scale I want to highlight that's often swept under the rug. That's what I call a trap-off time. So the way this is done is the following. So you load tweezers, but then once you start the Rootback physics, you actually switch off the tweezers. You do the Rootback physics very quickly, and then you switch the tweezers back on. So essentially, all the Rootback physics is usually done in a time of flight. So this time of flight has a certain time scale that's basically depends on what's your probability to recapture atoms afterwards. You cannot let them fly too long. And we usually do that because the Rootback states are extremely strongly anti-trapped. And we want to avoid this light shifts during the Rootback dynamics from the anti-trapping. That's why you switch it off to get in a very clean trapping state, basically, or non-trapping state. And this is basically the time you have to do physics. You have some sort of a decay time, and then you have some sort of a cutoff time that's set by this trap-off time. And you have to compare these time scales to typical achievable Rabi frequencies, and this is typically a few megahertz with alkali atoms. So this gives you an idea for how many operations you can do in this typical trap-off time, okay? And then there's additional limits in system size and also Rootback detection fidelity so far with alkali atoms hasn't been that good. And the detection usually actually works by expelling atoms out of the trap after you switch the tweezers back on. So Rootback states are anti-trapped. Once you switch the tweezers back on, you expel Rootback atoms, and you just detect what you have back in ground state atoms. That gives you a method to distinguish Rootback and ground state atoms, okay? Good, so these are the limitations. And then what I'll talk about for the rest of the talk is how can we potentially improve on this by using alkaline earth atoms? And are there maybe qualitatively different applications? But before I do that, maybe I can collect, a few questions, if there are any, about what I've been talking about so far.
So we have a couple of questions from our panelists here. So John Simon asks, does the 1D phase diagram change in the presence of both 1 over r to the 6th and 1 over r cubed dependence of the interaction? So for example, by going to higher principal quantum number or near a first order resonance?
Yeah, it will change for sure. The question is I think the question is maybe, does it qualitatively change? I guess, do you have new quantum phases? I think if the interaction term is still Ising type, that means it's only density. I think I would be surprised if something qualitatively changes, because that classical limit, which is when your Rabi frequency is very small, that's known. That thing won't change drastically, because that's usually this devil's staircase that you get, and that only depends on the interaction falling off. As long as it falls off, it will look exactly the same. If you have more Rabi frequency, if something changes, I don't know. I think something might change if you really go to XY type interactions. If you have spin exchange, then it will for sure change. I think then everything is you have to debate from scratch.
But you never get incommensurate physics.
You do already with 1 over r6 actually.
Oh, you do. Okay.
It's not shown in here. It's very small slivers, and that's something that's still under debate to a certain degree. But there's a paper by Leuchli, if you want to read that. It's cited in one of the slides, which shows where this incommensurate physics actually appears.
Great. So we have a couple of questions related to the necessity of turning off the tweezers. Mm-hmm. Shimon Kolkowitz asks, is it possible to also trap the Rydberg state, and would it be worth it to avoid the limited times infidelities associated with retrapping? And then I'll just add to that a question from Zheyoung Li, who asks, will cooling of the motional state help with retrapping more atoms?
Yeah. Okay, let me go step by step. So, I mean, if you can trap the Rydberg state, it will always help you. And ideally, you can trap it in some sort of a magic condition where it's trapped ground and Rydberg the same. However, I mean, it's really just a question of energy scales and so on. So if your Rabi frequency is very, very high, all of that actually doesn't matter. So if you're trapping trap depths you have and the motions that you have is much smaller than the Rabi frequency, it's all suppressed completely. And it's actually something we have seen. Later on, I will show some data for belt state generation, and we see that you get almost the same belt states if you keep the trap on. And the reason for that is that our anti-trapping, still anti-trapped in our case, but it's not as strong. But our Rabi frequency is very high, so you can just override everything. So that's one answer. So ideally, you would trap it, and that would give you less dephasing. Ideally, you would trap it in a magic configuration, and you would have no dephasing from that. And then you could do longer experiments. On the other hand, is that if you really do a many-body experiment, and I'll show that later, at least with current coherence times, you're typically limited by other things first. That's another thing. So that's one answer. And another way you can gain is really by just going to higher Rabi frequency. It just gives you more operations in that trap-off time. So that's the one answering maybe Shimon's question. Then the question from the audience. Yes, you get longer time of flight if you're much colder, and that's also what we're seeing. For us, actually, we use trap-off times for 20 to 30 microseconds at Caltech, because you can go ground state cool, and then you could do adiabatic cooling again too, and then you get longer time scales just from being better cooled. So that is true. Indeed.
Great. So there's one other question. I think you'll probably get to this, but I'll just put it out there in case you want to make a comment. So the question was, considering how short the coherence time is, how is it possible to study dynamics of the system or the time evolution? And perhaps you'll get to that in the course of your talk, but if you want to make a comment on that, that might be interesting.
I mean, that's like coherence time doesn't have a unique definition to start with, so I don't know how to answer it. So it depends on what you're asking. And I'll come back to some of these things. So we have a Rabi coherence time that we show, and we have a certain, Ramsey coherence time that you can show. Then you can talk about many-body coherence time. So these are all actually different. And all of them have different limits. They're limited. The fidelity is limited differently at short and long times, and so on is quite different. So typically it's a few microseconds, effectively. 10 microseconds, something like that. So it's on the order of this trap-off time, essentially.
Great. Yeah, so I think you'll be telling us more anyway, so I will let you continue and hope that everybody keeps typing in questions for the next break.
Yes. The next track might come a little earlier. Maybe we'll do it later. So okay. Anyway, let me go on. So as said, what we work on at Caltech is now applying these techniques to alkaline earth atoms, which have 2 valence electrons and have a more complex level structure. So basically, we have broad lines and a set of narrow lines and ultra narrow lines here that are normally exploited in optical clocks. Okay, so this usually is some sort of the standard application for alkaline earth atoms. And our goal now is to really study alkaline earth atoms in Tweezer arrays and make use of this level structure for our purposes. I should say we're not the only ones doing that. There's a history of that. So there's experiments of, say, ytterbium in quantum gas microscopes where people reach, say, single atom readout in these systems. So this has been done before us. And then there's, of course, also the past years have some sort of a nice back and forth between Adam's group at Schiller, Jeff's group at Princeton, and my own group. So many of the results I'll present have some sort of a counterpart in one or both of their groups. So I'll get to that. So I'll walk you through some of the results we have and some of the features. I'll talk about narrow line cooling using the 7 kilohertz line. I'll show you some results for high fidelity imaging. And then I'll talk a little bit more in detail about our single photon Rootback excitation scheme and the results we have there. And I will very briefly talk about the clock control only. And for the experts, all of the results I'm showing are for strontium 88. So that's the boson, which has no nuclear spin. Okay. So let me jump in. Okay, so the first piece is narrow line cooling. So there is this 7 kilohertz transition, and the first thing to note is that the trap frequencies in tweezers, at least on the transverse direction, are much larger than 7 kilohertz. So they're typically 100 kilohertz. So because of that, you can individually resolve them. And if you have atoms close to a magic trapping condition, you can basically do traditional sideband cooling. And here's a sideband cooling spectra from our group, where you see a very strongly suppressed red sideband, so you can cool very close to the motion at ground state. The atom is quite a bit better than we are with that. But essentially, you can use that traceability and then go very quick. The scheme we use is usually a little bit different. What we use is what I call a narrow line Sisyphus cooling scheme. And that is a situation where the ground state here and the excited state here have a different trapping potential. And the case I'm showing here is where the excited state has a stronger trapping potential. And again, one has to notice energy scales here. So these tweezer traps can be megahertz deep or multiple megahertz, even tens of megahertz deep. And you can also have a trap mismatch that can be multiple megahertz or tens of megahertz. And because of that, and because your line is so narrow, you can basically address a very narrow energy shell in these tweezers by just frequency tuning. So in particular, you could tune this laser such that it hits basically just the bottom of the tweezer. So you only get excited when you're on the bottom, but you don't get excited when you're further out. And then you can have a situation that leads to really just a textbook to Sisyphus cooling in a way. So atom rolls down, the bottom potential gets excited with the laser, rolls up, a steeper potential gets de-excited by a spontaneous emission in a very comic sense. And so this is really textbook Sisyphus. You basically lose energy in that process. And that's something we're exploiting all the time. And we noticed that the Sisyphus cooling is extremely robust in many ways. So one thing we really like about it is that you only need one laser beam. So we have a tweezer and we shine in only one beam from the side and it cools in all three directions. And the reason for that is that basically all the recoil comes from the trap itself. It doesn't come from the laser. So this is why this works so well. And so in essence, what we found is robust and simple cooling schemes that bring us close to the motional ground state. And it's pretty important for Rootback coherence to really suppress Doppler shifts. It's important for imaging fidelity, and it's also important for clock line control. Okay. So we use this cooling scheme during imaging. So how do we do that? So we cool atoms and then we scatter photons from a different transition, and these photons that we scatter are from this blue transition as 30 megahertz, and these are the ones we collect. So these are blue photons, and this scheme where you have cooling and imaging on different transitions gives you more flexibility, but it also enables higher scattering rates because that 7 kilohertz is actually quite limiting. Here are some results. So there's a single shot and an average image. So this looks very good. So what you can do now is you can make basically a little box around an atom here, and you can basically plot some photon statistics that you achieve in this box. And what you see is a very nice peak for no atoms, and then you have a very nicely separated peak for one atom. And what I don't showing here is if you would go further out, you don't see additional peaks. So 2 atoms you never observe, basically. And importantly, these 2 peaks are very nicely separated. This enables you basically just call a threshold here and say, okay, if I'm above that threshold, I have 1 atom. If I'm below that threshold, I have 0 atoms. And this defines some sort of the accuracy of how well separated are these 2 peaks. And with this, you can quote a fidelity. Fidelity is actually the wrong word. It should be called accuracy. That's the right word. But essentially, this is how accurate am I in distinguishing 0 from 1 atom. And this we can do with up to 4 nines here. Okay, that's one number. There's another number that's very important. That's the survival probability. This is, okay, I take an image. What's the probability I still have the atom in the next image, right? Like I want the atom also to survive in many of the circumstances. And this is, for us, 3 nines. And these 2 numbers are very important, say, for atom by atom assembly. I'll come back to this in a second. So the key to get these numbers in our case is, one, you have to be able to cool very well during imaging. That's true for everyone in a sense. And in our case, what we found is that it's important to have extremely long lifetimes. That's just how it is. And we see that we have 7 minutes lifetime by just cooling and without that blue beam on. And if you switch the blue beam on, depending on the configuration, it's about a minute lifetime. And this number basically sets these numbers essentially if you really go through the math. Okay, so these are both extremely long here, and then these numbers are also pretty high and much higher than what's usually done with tweezers at least. And these are important again for atom by atom assembly because of that scaling here that I showed you earlier, because that scaling also includes imaging fidelity and survival fidelity. So you have to be correct in identifying an atom, and you're not supposed to lose it in the meantime. And in terms of just the fidelities and the survival rates, now we can go basically to a total success probability of 50% for around 1,000 atoms. So this would really enable large-scale atom by atom assembly if you could achieve that also in the shuffling around of the atoms. Okay, and it's also important to have high fidelity imaging for debugging high fidelity quantum operations, and I'll come back to this in a second. Okay, so I'll talk about the single photon Rootback scheme now. I think the questions break here might come a little early, if there's, or should I take questions? Monica, what do you think?
Well, there is a question from Ivan Deutsch, who asks, what are the limits of the local Sisyphus cooling as compared to resolved sideband cooling? And how cold can you get in one method compared to the other?
Yeah. Hi, Ivan. It's good to hear from you. So Ivan is, of course, an expert on that. He has wrote one of the first papers on narrow line Sisyphus cooling, as I learned recently. So yeah, it's very hard to say. So if it was just Sisyphus cooling, in a sense, and it's all clean, you can only drive in a quantum mechanical picture every second sideband because of basically symmetries. But it's not that simple, because once you're very cold in a tweezer, it doesn't matter anymore. Then you're only addressing, say, from the 0 level to the first level or so. So it's very, very, it's only a few levels that you're addressing. And then the trap mismatch doesn't matter anymore. So what in effect, what really happens is that like when you're hot, Sisyphus cooling dominates and it brings it down to be cold. And when you're cold, you can actually really do resolved sideband cooling again to a certain degree. So, and then in terms of what's your limit, it depends on how much mismatch you have in the trap, I think. And in the end, like, I don't think that's the limiting case. For us, I think what we're learning is the sideband cooling is limited by basically by laser frequency noise and also by misalignment of the beams. So that's all I can say. So I don't really know what the practical limitation differences are. And maybe the one take-home message is that these things don't happen independently if you really look into it. So if you start Sisyphus cooling, you also have sideband cooling at the same time, basically, as soon as you get cold. So that's the practical answer.
Great. So we also have a question from Yuting Chen about the high fidelity imaging. Yuting asks, what limits the width of the N-atom signal and what are the ways to reduce it?
The width. Okay, there's of course noise on the camera that gives you certain, that's one. I actually don't know what the dominating factor is. We never really explored that. I mean, you also have of course, a shot noise because like you have a certain finite angle, and it's like, okay, it depends on where your photon goes if you actually observe it. So if you had, I think if you had a higher NA, actually that would reduce it if you actually reach that limit, or a better camera. In practice, like what you really want is you want to observe a lot of photons. That always helps you. So that's what you want. So you want to get a lot of photons detected. And then like, how do you do that? You want to have higher scattering rate. That means you need better cooling. That's one way. The other one is to just go to a higher NA. Or to use two objectives. Actually, some of the data I've shown, we use both objectives. It's a trick. So you take both objectives. And then what we do is we just place a mirror on the top objective that reflects the photons back down. It goes back through somehow a little bit above, like from the side from the atoms, and then goes through the other objective, and they both go in the same camera. There you can, if you're lucky, double your photon collection rate. It's a trick. Stuff like
Great. So I'll let you continue. And we have a couple more questions coming in, but we'll have other opportunities. So.
Yeah, more time. Yeah. Okay, great. Let me continue with the single photon excitation scheme. So, okay, so here's the level diagram again, including Rootback levels. So essentially, you start out in this true ground state down here as 1 as 0. And what we do for Rootback excitation is we move atoms to 3p0 with a metastable state. And we do this via clock line excitation. And I'll show you later how it works, actually. Just believe me that we can do it. And now this metastable state, it essentially lives forever on the time scale that you would need to do the Rootback physics. And now for this Rootback Hamiltonian, I showed you what we do is we basically call this our new ground state and then have the Rootback state as our excited state. And this looks like a 3-level scheme, but in essence, we basically avoided that intermediate step. So this somehow avoids this intermediate scattering, and now you're basically down to a true 2-level system here, okay, at least for the time scale of how long this metastable state lives. And there's multiple advantages here. So first off, you can get higher Rabi frequencies at smaller intermediate state scattering. And you can also reach higher Rabi frequencies because, high Rabi frequencies in general, because at 317 nanometer, you can get relatively high power lasers. Okay, so this basically replaces this 2-photon excitation scheme in alkali atoms. The atoms are very hot, so very close to the ground, very cold, I should say, very close to the ground state. So our Doppler dephasing is actually completely negligible for all of our results that I'm showing in a second. And then what I showed you before is that we have very high detection efficiency for basically ground state. It's true also for 3p0 and this 1s0. And we also have a new detection scheme for Rootback states, which improves on this 98% typical detection efficiency for Rootback states using auto-ionization, which is pretty easy in alkaline earth atoms. And finally, coming back to one of the questions that was asked, the Rootback states in alkaline earth atoms are in principle trappable by using the strontium ion core. So these Rootback states that I'm showing here, you have 2 electrons. One is in a Rootback state, and one is close to the core. And that core forms a strontium plus ion. This has optical transitions, and these optical transitions you can use for trapping. We haven't really done that like in detail, but Jeff has done that at Princeton. He has a really nice paper on that, and I suggest to look at that. Okay, so let me start. So what we did first is just to try to look at Rabi oscillation. So we prepare all the atoms here. We prepare atoms in an array. We prepare them at distances such that they don't interact, such that you should see very nice 2-level physics, essentially. We go to n equals 61, and we try to hit 0 detuning to just see very standard Rabi oscillation. And here's a typical result. If this is 1, you're basically in the ground state. If it goes down to 0, you're in the Rootback state. So you see very textbook Rabi oscillations here. You see also on longer time scales a nice Rabi oscillation. So we see up to 40 or so oscillations here. I should say this is probably the first Rootback Rabi oscillations with single alkaline earth atoms that we observed there. We reach Rabi frequencies from 6 to 15 megahertz. We could go even a little bit higher, but it becomes really hard to control. The pi and 2 pi fidelities are typically 99.5, and that is without correcting for any preparation and detection error. So this is really the bare numbers we get. Also, these graphs are all raw data essentially, so we didn't do any correction. And then we have oscillation visible, so typically 40 oscillations. And so the long-term coherence, that's maybe to answer one of the questions. So how many oscillations can you see? This is completely dominated by intensity noise actually in the laser. So this is noise on omega that sets how many you can see out here. That's one thing we know. There's something we don't know, but this one we know for sure. Okay, so that also means that if you go to higher Rabi frequencies, you cannot increase the number of cycles you can observe because it all scales relatively essentially. Okay, good. What about interactions? So this looks very nice. So we can do the single particle physics. So to really observe interactions, we go into a typical blockade regime. So to do that, the best is to really sort atoms into pairs. Within a pair, atoms are strongly interacting, and then the pairs are spaced such that pairs don't interact with each other. So you get a copy of pairs that interact strongly. Now, the physics is the following. If an atom is far away, you get standard Rabi oscillations because you're just on resonance with these 4 levels. You have ground, 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 Rootback, Rootback, ground, and Rootback, Rootback. These are the levels of the 2 atoms, basically. If you go closer together, you see a strong shift of the doubly excited state from this van der Waals interaction that I showed you. So this is this 1/6 term here. And what you see is that the excitation from the single excited state to a double excited state is blocked as long as your Rabi frequency is not too high. And that's a typical Rootback blockade. And now, if you really look into a bit more detail, is what you see is that the Hamiltonian, because of symmetries, excites from a ground-ground state to a superposition state of this ground Rootback state. And at the same time, you should see an increase in Rabi frequency by a square root of 2 if everything is correct. Okay, so we observed that in that configuration. So I'm not showing the square root of 2 increasement, but it's there. You can measure the Rabi frequency with that larger spacing and the small spacing. You see exactly a square root of 2, and you see these very nice Rabi oscillations from basically being in the ground state. And this down here is when you have population only in these levels. Okay, so very nice oscillations. You see very long time coherence, even more oscillations than before. We see up to 60 of these blockade oscillations actually, again dominated by amplitude noise. And again, I think these are the first Rootback blockade oscillations with alkaline earth atoms. Then we also have a method to basically try to extract the Bell state fidelity. So this method gives you only a lower bound and is actually relatively conservative in how it does it. So essentially, we look at the populations here to determine how well we reach the right levels. And you can look at the population here to get a lower bound on the purity of the state actually. And this is not completely trivial how to do it, but that's how we do it. And with this, you can get a lower bound on the Bell state fidelity. And the Bell state fidelities we find, lower bounds are 98% roughly without correcting for anything, and then 99.5 with correcting for state preparation measurement errors. And these are quite large numbers for neutral atoms, I should say. And so this 99.5 somehow reach numbers you would see in superconducting qubits and so on. But of course, I should say this is only in this ground Rootback state manifold. It's not universal gates and a long-lived ground state transition. So this is some sort of the next state. But I think these numbers give you an indication about various things. I think we should be able to do pretty high fidelity quantum simulation with that. That's one. The other one is the Rootback coherence that you have to generate entanglement for a gate should be pretty good. And you shouldn't be much worse than this number in a gate if you do everything right. So I think you can actually do gates that have this type of fidelity. 2 qubit gates, that's what I'm saying. And in the end, we really want to use entanglement also for quantum metrology. Okay, so this is something I'll come back to. Okay, I can talk a bit maybe later about limitations and so on. So I skip this for a second. So what do we actually think is limiting? I want to say one thing about how we do the detection. I think that's interesting in itself and also might open up a new research avenue. So again, the way this is usually done in alkali atoms is you do the time of flight and then you switch the tweezer array back on, and then Rootback atoms get basically expelled from the tweezer. And then when you detect an atom in the tweezer after switching it back on, you would interpret it as a ground state atom. Okay, this has a finite detection fidelity for Rootback states because the atoms can decay back down in the ground state during this expulsion process, which is kind of slow actually. And this gives you this relatively, it's good detection fidelity, but not super high, this 98% that you usually see. What we do is somewhat similar. So we also use a loss-based scheme, but instead of relying on tweezers to pull the atoms out, we convert Rootback atoms very quickly to ions. And then these ions don't appear in the image anymore. So you basically can distinguish ground and Rootbacks by that. Okay. So how do we do that? So we do this via autoionization. So again, these strontium Rootback atoms have one electron in a Rootback state, and one electron is very close to the core, forming a strontium plus ion. You optically excite the strontium plus ion, and then you are in a doubly excited state that's very rapidly autoionizing, and the outer electron gets expelled, and then you basically left over with an ion. So in particular, this scheme is extremely fast compared to the Rootback lifetime. And then just based on measurements we have from these Rabi oscillations, we can put a lower bound on the detection fidelity. It's something like 99.6. And there's an upper bound we quote sometimes that comes from a comparison of the time scale of this autoionization process and the Rootback lifetime, which is 4 9s and a 6. So that's somehow how good you can get with the current Rabi frequency of this autoionization laser. You could be better if you have more power and so on. And that's actually what we use to get this really nice curves without any kind of post-processing. Okay. I should say that this is interesting, not just because it helped us to increase the fidelity, but you could also think about what happens with the ions now. So these ions in the wavelengths that we use for tweezer trapping should actually be trapped. So they are trapped via optical transitions in this strontium plus. And one question is if these ions actually survive in the tweezer array, and we've done a lot of math on that. I think in our case, they don't because of electric fields, because we don't have very good electric field control. But I think if you have somewhat decent electric field control, these ions should be still in the tweezer. And that's what I'm saying is that if this is true, this would give you a new pathway to actually generate basically optically trapped ions. You just trap neutral atoms, autoionize them, and then you should have an optically trapped strontium plus if you do it right with good electric field control. Okay, that's one comment. Okay, let me go on and talk about clock states very quickly. So I said that we can move atoms from the ground state to the clock state. So how do we do that? So we are in strontium 88, and for the experts, the clock transition is nominally forbidden in there, but you can make it allowed by putting it in a very strong magnetic field that essentially generates an admixture of a 3p1 state into 3p0, so you get a little bit of the 7 kilohertz line width that makes it allowed. So in this very strong magnetic field, we see Rabi oscillations with a few kilohertz, usually 5 kilohertz or something like that, and that's kind of old data actually. So we can achieve 99% transfer just coherently, and then for the rest, we basically optically pump everything up. And we do it coherently because the coherent transfer is better in terms of temperature, so you don't heat the atoms up. But in contrast to optical pumping, where you basically scatter a bunch of photons, so you want to keep them very cool. So this is how we do that. But you can also ask, of course, if you tune down this magnetic field and you make this line a lot narrower, basically controlling your Rabi frequency on. So what's the minimal line width you can achieve? And can you build a clock out of this? Essentially, that's the same thing you would do in an optical clock, in an optical lattice clock. And we did that, and also Adam, of course, did that, and I think he gave a talk about this a few weeks ago. And they're somewhat the experts on this, I should say. But we also did it, I should say, and I want to briefly explain it. So we basically stabilize a narrow line laser to an atomic signal from tweezers that comes from individual atom readout, and you basically feedback an error signal onto an AOM that controls basically the frequency of that clock laser. And I don't want to say a lot of things about it, but I think that graph is some sort of indicator of what's going on in the field. So you see we have 80 tweezers, and for each of these tweezers, we get a Hertz level type error signal. And I think this is very remarkable in the sense that you could actually see something like that. And to me, this signals some sort of a marriage of a precision measurement, optical precision measurement, and single atom control in many body systems at the same time. And I think this marriage will go further than just tweezer arrays. I think tweezer arrays and tweezer clocks have some future, and we'll have to see how far we can go, but I think it goes further than that. So I know one group, for example, who is actually planning to trap hydrogen in tweezers to build an optical frequency standard via hydrogen, for example. That's one example. I know that people thinking about EDM measurements are thinking about tweezer trapping of molecules for that and so on. So I think there will be a lot more in this direction that really combines really single atom control techniques where you have large scale systems with precision measurement. And at the same time, in our case, the system is somewhat programmable already. And we have very high fidelity means to generate entanglement. So you could naturally ask about quantum metrology in that system. And that's something we're thinking about. And to this end, let me zoom out a little bit. So I showed you this Rootback state control via this G to R transition here, which defines one qubit. And that's very useful, I think, for many many applications in quantum simulation where you just study Hamiltonians and certain things. It's also something that we're looking at in the context of quantum optimization concerning this maximum independent set story. Then I told you a little bit about the clock only. So you could use it as a qubit in principle, or you use it in a clock context for basically precision measurement type ideas. And then you could combine both things in sort of a three-level system that you have to control. And then you can ask about gates in clock states or even in nuclear states down here. And you can ask about quantum metrology. So could you use Rootback excitations to spread entanglement in a way that is useful for clock operation? Okay, that's one question we're looking at. Okay, so with this, I would like to summarize and give a very brief outlook. I showed you results for arrays of alkaline earth atoms and narrow line cooling. And I should say for most of these results, again, you find some paper in Adams or Jeff's library now. I don't want to cite them all. So this is this. I showed you some results on high fidelity imaging and long lifetime, where we see 7 minutes lifetime and like really high, many nines fidelities for imaging and so on. I showed you some quite new results on Rootback state control in alkaline earth atoms, very nice Rabi frequency oscillations, high fidelity detection, and also very high values for Bell state generation. And finally, I showed you our results on basically building a tweezer clock out of this whole story. Okay. So the outlook is essentially to make use of entanglement in the systems for simulation, metrology, and optimization. And I want to show maybe one slide of preliminary results for quantum simulation that are mostly still before COVID shutdown, unfortunately. So we were shut down for many, many months now, and you're just ramping up now. So basically, this has been a bit of a problem, but we have a few results that are kind of interesting. So one thing is we can do atom by atom assembly in 1D now with alkaline earth atoms, and we reach defect-free arrays of about 60 atoms if all lasers behave well. Okay, so this is one thing. We use these 1D arrays to study physics in various scenarios. So the one is that, like, most of the experiments we have done are quench experiments. You start with all atoms in the ground state, and then you just quench with this Hamiltonian that I showed you. And again, this Hamiltonian is so rich that you can tune it to different types of regimes. And we did that. So one regime you can actually reach is a close to integrable regime. And then in an integrable regime, basically quasi-particles should be free to move. And these free movements of quasi-particles should result in a light cone spreading of correlations. And that's something we observed very nicely here. So this is experimental data for a 2-point correlation function, where you see a very, very nice light cone as a function of distance as time in this correlation function propagating outwards. So that's one thing. And it fits very nicely simulation data. So this is in an integrable regime, and then you could play with this a little bit more to see more complicated effects like confinement, for example, and so on. You can also tune it to a chaotic regime where quasi-particles are just strongly interacting, and there you should see coherent thermalization in a sense. And we have seen some of that. So what you see is like a simple observable. This is local sigma c, for example, and you see some oscillation, but then it plateaus out, and it plateaus out exactly at the value you would expect, basically from prediction from a thermalization picture. Okay, so this is very nice. What you also see is that the experimental data here, these blue black dots, follow very nicely an exact diagonalization simulation up to some very fine-grained details down here. So this is also very good. So in general, what we see is if we do many-body experiments and we look at somewhat local observables or two-body observables or low-order observables, we see extremely good matches between what we do experimentally and what we predict via, say, exact diagonalization. Okay. So this is one news. The other question we started to ask, and that's some sort of a question I've had in my mind for many, many years since I was a PhD student, it's the following. So can you actually measure fidelity on a global level for many body states? That's something that's actually important, I believe. So the idea is the following. So you have an ideal target state, you do some quantum evolution, and that's a pure state that you would generate on your computer, for example, in numerics. So that's what I want to reach. And then you have an experimental state that's somehow dominated by the coherent dynamics, but also by all kinds of dephasing mechanisms that you have. And then you can ask yourself, what's actually my fidelity, my probability to reach that state, basically, so to have no error. So this is a many-body fidelity down here, this quantity. Can you actually measure this? And it turns out that in chaotic dynamics, you can. To a certain degree, and this is what we did. And I think the first group who did that is probably the Google group in a random circuit. So what they did, they apply random circuits, and they apply so many random circuits that they basically are in a regime where the system is completely scrambled. So it's completely thermalized. And then in that regime, you just sample in a one basis, and then from this one basis sampling, if you do it right, you can extract the probability you had to make an error on the way of reaching that regime. So that's essentially the same thing as this fidelity. Now, it turns out what we learned recently is that you don't even have to go through this full thermalization regime. You can do this at much earlier times, and it also works for analog quantum simulation if you modify the formulas correctly. And this is some of these results. So we know now that you can have a fidelity estimator that estimates this fidelity during chaotic dynamics just by sampling and sampling correctly. And this is this blue dots. This has some sort of a moving average to a certain degree, but it's quite noisy because we, at the time where we took that data, we didn't even know that we can do that. And we didn't take enough snapshots, but this is the experimental data and it decays down. So this is an estimator of this fidelity, it has a certain decay time. And the other curves you see there are also quite interesting. So this dashed line here is a many-body model that we wrote. That's actually an open system dynamics model that includes all kinds of errors, preparation error, detection errors, spontaneous emission of various kinds, laser noise with realistic power spectral densities, and so on. And the tricky part is that this is non-Markovian, so you actually have to run a quantum jump approach on a many-body level correctly. And what you see is that we can correct that, we can predict that fidelity decay correctly, basically using a priori measured quantities that enter this error model. And that's very nice on one hand. So this is this blue line that predicts this fidelity estimator. And then the red line is the true many-body overlap in that quantum state that you predict with your many-body model. So I predict a row with my model, and I look at the true fidelity. What you see is that this estimator follows the true fidelity very nicely, even if we don't average over different circuits and stuff like this. So there's some sort of a typicality that happens in there. So this is actually what we're working on right now, and we want to push this to larger system size and understand certain things a little bit better. And one thing I want to say is that coming back to the very beginning of the talk when I told you, okay, it's actually hard to make no error in many-body dynamics. So this is this curve down here, right? You see the fidelity goes down, and then we also have some system size scaling, and you see the scaling of how fast it goes down is exponential in your system size, essentially. And at the same time, you can ask yourself, okay, this time scale here is somewhat arbitrary if you don't give me some sort of a notion of what you're doing in that time scale. But you can get a notion for that if you look at entanglement entropy. Because I know the target state now and I know the fidelity of reaching the target state, I can look at the entanglement entropy in that target state to get a bit of an idea. And this is this yellow curve here. So this yellow curve shows you for that dynamic, the entanglement built up in the target state, and you get a little bit of an idea. So this would normally saturate up here, and you see that when we reach close to saturation, we have around 50% fidelity still. And you can ask further questions. You can ask questions, okay, can you use that to really construct a mixed state entanglement measure or lower bound for that? And the answer is yes, and it's something we're working on. So you can take basically this curve and the yellow curve, and if you do it right, you get another curve that would look like this, that would basically give you a lower bound on the true mixed state entanglement in this row. Actually, this is quite interesting. So we could really measure that now via this approach. Okay. And with this, I'm going to back up. So I think something that really I want to get at with the experiments we're doing is to do some sort of a certified quantum simulation, certified in the sense that I know what my fidelity is, in regimes that become increasingly intractable via classical algorithms. So I really know what our fidelities are. And in particular, this approach does not only tell you about decoherence, it also tells you about how well do you know your Hamiltonian. Because it turns out if you make a mistake in your Hamiltonian in predicting that target state, this curve goes down very, very quickly. So we also in turn use these curves to calibrate our Hamiltonians correctly to see if we have corrections in them. And I think this is a very nice strategy to really make progress in quantum simulation, such that we think our results are convincing in a sense on a quantitative level. Okay, so this is really what we're working on. And with this, I would like to wrap up and thank you all for your attention.
Thanks, Manuel, for a really great talk. So we have a number of questions here. I'll start with a question from Manuel Morgado from YouTube, which is whether you could tell us actually what the pi and 2 pi fidelities are for the single qubit Pauli operations in your system.
The one I quoted were uncorrected. So if you don't correct for detection error, it's 99.5. I actually don't remember the ones for correcting detection errors. It's higher, it's 3 nines or something like that. Yeah. It's in the paper. If you open the paper, it's on the first table. I can open it up. I don't remember exactly the numbers, but it's 3 nines upwards. Yeah.
So yeah, so then following up on the fidelities, actually Shimon Kolkowitz asks the fidelities for Rydberg gates, or actually the Bell state fidelities that you've demonstrated with strontium, are higher than what had previously been demonstrated with alkali atoms. So what are the main advantages with alkaline earth atoms that enable these high fidelities? Is it the narrow line cooling, better atom and state detection? Is it fundamental?
I would like to know that too. I should say that I think, if I'm really honest, so if Misha, Harry and these guys, they would go ahead and try this again, it's exactly the same method. And with the coherences they have now, I think it would be quite close to that. So, I mean, one thing is that you want like very high Rabi frequency. This always helps you in a sense for the short times. You want to be very fast compared to spontaneous emission and all that stuff. And then that is that. I'm not sure anymore if the alkaline earth like helps you tremendously. If you really just want to go to super high fidelities with alkali atoms, I think you can do it if you do it right. Like in particular, there was a development for high power lasers for the upper arm in this 2-photon transition. If you have very high power there, and then you control everything extremely well, the two polarization gradient cooling very well, and so on, it should be okay. It's mainly a question of laser noise in the end, and controlling things precisely. So I believe there's no reason to believe that you can only do this with alkaline earth atoms. What I can say is that it has been not easy, but not super hard in the end with alkaline earth atoms. So we don't even do additional phase noise filtering and all that stuff. So Misha, they do super complicated phase noise filtering protocols. We don't even do that. So they might be even higher if we do that. So like it wasn't that hard in the end. So maybe that's one indication. So I think once we learned how to cool everything, the Rootback piece actually went together quite easily and quite fast. One advantage that I see is actually preparation error. So we don't have any hyperfine states around. So we just put the atoms there. So you can prepare with very high fidelity and have the readout. The readout also helps you in making things easy. So I'm not sure if this was a good answer, but like it's very hard to tell, I would say. The one thing that helps you is high Rabi frequency. That's the thing I can always say. So this thing, the higher your Rabi frequency, the better. So that stuff, that's clear. And this is relatively easy to reach fast. So we don't do anything fancy. We don't even have a super high power laser, actually. It's like you can go like order of magnitude higher in power.
So I'll also just kind of paraphrase a couple of questions that came up relating to, can you maybe comment on the relationship between the Bell state fidelity that you showed us and implementing a 2-qubit gate and 2-qubit gate fidelities in your system?
Yeah, okay, let me do that. So it's hard to tell. These are different things, right? I mean, so the question is to start with, what kind of gate do you want to make? So ideally what you want to do is you want a gate in a long-lived ground state qubit. So that's not what we're doing here. So our entanglement is in the ground to Rootback qubit. So that's the first important piece of information. So now what you want is entanglement generated in the ground state qubit. And then for this, of course, you control fidelities of a ground state qubit enter as well, additionally. Okay. So this will reduce your fidelity. And then at the same time, I think if your ground state qubit control fidelity would be 100%, let's assume that for a second for simplicity. And then you would go through and do some sort of like a randomized benchmarking or whatever on that gate that you generate here, using basically single qubit control on the ground state plus some entanglement piece on the Rootback state. I talked quite a bit about this with Hannes Pichler, who is a little bit of an expert on that, and who also actually, I think, invented the best gate for that purpose. It's sometimes called the Pichler gate now, if you haven't heard about that. So that's the gate the Harvard guys use. So it's a very nice idea. And if you did that and your control and switching on the pulses of the Rootback pulses are well, the fidelity that you get should be better than the 1 pico, actually. I think this Bell fidelity is actually if you do randomized benchmarking on the ground state, it should be better, actually. Assuming two pieces. One is that the ground state control fidelity is like 100%, and that you're very good in applying that Pichler gate, which is a little bit more complicated than what we did. So I think maybe where this points to is really the outlook of like how well can you do, say, digital quantum computing with neutral atoms. I mean, that's a question, right? That every one of us would like to know. So I don't know, but what I think is that there's no reason to believe that the fidelities you can reach should be any lower than that number. That's what I believe. And that number, I have to say, if you look into the history of gates, really full 2-qubit gates, if you look at superconducting qubits and so on, no one has reached fidelities that are actually higher than that. I think the record is 99.7 for superconducting qubits. And then for ions, it depends on how many ions you have in the chain. But in our case, these are 10 pairs, so it's 20 atoms, right? So, and I don't think in a 20 ion chain, anyone has reached a fidelity like that for a 2-qubit gate. So we haven't done that either. So I'm not saying that, but what I'm saying is that with the fidelities we see in this ground to Rootback control, if you had extremely high ground state control fidelities, which some people have reached, if you look at what, say, Dave Weiss has extremely high fidelities, I think you should be able to do a gate that has this fidelity or better. That's my prediction. And I don't think this will take a very long time. I think within the upcoming 2-3 years, someone will do that.
Great. That's a very exciting prospect. So let's see. I'll ask a technical question here from Zheyang Li, which is your tweezer in the magic wavelength for the clock transition? And if not, would your tweezer intensity fluctuation affect your experiments?
Yeah, so we work in 813, so we work in magic wavelengths for the clock. That answers the question. And if it wasn't the magic wavelengths, the clock transfer and all the clock control would have lower fidelity. But I think that's, maybe let me rephrase it. The other question is this what you want to do long term? And probably that's not what you want to do, because this 813 is not particularly scalable. So you cannot go to really, really high tweezer numbers. Either you can do build-up cavities as the other solution, but I think what you want to do long term is have one array with some convenient wavelengths just for the imaging part, and then have a loaded into a tweezer array for the clock control part, and then read out in another one. It's kind of what Adam does already in a certain degree. But then the imaging part, for this, you really need very, very deep tweezers. This is what makes it so hard to scale. For the clock control part, your tweezers don't have to be particularly deep, but you could do it even in a lattice. So I think eventually there will be like a 2 wavelengths design where you like have 2 types of tweezers where you go back and forth, or like 2 sets of traps. I think one might be a tweezer and the other one might be a lattice, actually. That's I think the end goal there.
Great. So I'll come now to a pair of questions about ion trapping in tweezers. So John Simon asks what level of field control would be necessary for ion trapping, and Mingyu Fan asks for the strontium ions after auto-ionization, could the Coulomb potential between ions and nearby traps push them out?
Yeah, let me answer the second question first. Yes, of course, if you put them very close. Coulomb forces is something I learned. I've never worked with ions, but once we plotted a Coulomb force for the first time on top of tweezer potentials, I was quite shocked, I have to say. This is very, very large. And it's very steep. So you actually, you have to have very deep tweezers at reasonable distances. So there's a limit, okay? And I think this is also the reason why I didn't put a lot of effort into it eventually, because you can make some estimates if you want to do it just in a tweezer. You need extremely deep tweezers, and then if you can think about gates between ions and so on. There are proposals for that from Ignacio with everything. You find a paper from Ignacio from 20 years ago, but he thought about that. And he gives you a number for spontaneous emission and so on. And then if you really think about gates, the gates, I think if you just use tweezers, cannot be extremely good. You get a limit of 98 or so, 99% fidelity. That's it. So that is the limit in terms of distances and how deep you have to make tweezers. And then field control, again, also depends on how deep you can make your tweezers, to be honest. So it's the same. The field control question is the same question as ion, because it's a Coulomb potential, and you just have to look at the electric field that you have from a nearby ion. I don't remember the numbers exactly. What we mainly looked at is, can we at least see a transient signal of an ion, even if it's not fully trapped while it flies away. And at least with what is a volt of per centimeter or something, what we have, you cannot for sure. Maybe you can, but it will be hard. Let's put it like that. We could do it using Rootback. So you could use Rootback excitation to detect if there's an ion via Stark shifts on the Rootback, for example. That's something we thought about. We kind of stopped going there. Maybe we would see something, but with the current apparatus, we wouldn't be able to go very far, I think, because first off, you need electric field control that's actually dedicated, and we don't have any electric field control in our system. And the other thing is, you might really have to think about the trapping more carefully by combining tweezers or some optical trap with an electric trap in a clever way. So if you want to do it, I think it's better to build really a new experiment. But it could be quite funny, and I think the really interesting part of that is not to make gates or so with it ions. I think that's almost boring, honestly. So I think the interesting part would be to check, for example, if electrons can hop between ions. That's something we thought about a lot. So if you have two ions, and then like you ionize one of them, and then the other one you don't ionize it, but you keep the electron in the Rootback state. And then if you what we know from like calculations that we did, or actually Chris Green did together with us basically, is that if you bring them close enough, basically the electron can tunnel back and forth. This would be cool. Say you have two ions at a micrometer distance, and you could see the electron tunneling going forth, back and forth. This would be really a completely new thing to study, like atoms and ions together. And then you could make arrays and have some kind of little metal where atoms could tunnel forth. But I think it's also pretty tricky to do that because this excitation and the motion of the electron is very strongly coupled to the trapping of the ion core, actually. And that gives you very weird features of trapping sidebands and so on. I think it's quite complicated, but that would be the funny part. That I would be excited about that, to do that. But just to trap ions for computing and so on is a little bit skeptical that this would. I have no reason to believe that this would be better than Rootback. Let's put it like that.
Great. So I will now come to a question about the quantum simulation part. So Yuting Chen asks, how is the entanglement entropy measured? Do you have two copies of the system, or is it measured by randomized measurements?
Oh, maybe I was not clear about that. So the entanglement entropy here is not measured at all. Okay, to be clear. So what's plotted here is the entanglement entropy from theory from that target state that I have. The only information I have is an estimator for the overlap of my experimental state with that target state. That is the blue curve here. Then now you can believe me or not about this estimator. That's a different story. There's some limits to that, but I think we are in a regime where this actually works very well. So I think we have an estimator for that. So now what you have is a target state, and I have overlap with that target state. So now I can plot the entanglement entropy in that target state and just plot it. That's one thing. A more complicated question is, given the entanglement in the target state and the overlap, can you construct a lower bound for the entanglement in your mixed state? That's maybe what you want to know. And that's a little bit more complicated, but the answer is yes. I haven't shown it yet. That's something we just figured out very recently that you can. So that is a true lower bound for mixed state entanglement. And mixed state entanglement, I should say, is usually not measured. So even if you measure it with copies, you wouldn't know that, I think, actually. It's kind of tricky, actually. You know the entanglement entropy. The entanglement entropy for mixed state is not the same as an entanglement measure for mixed state. You typically have to go through what's called a convex roof construction. So you have to optimize over all pure state decompositions of a mixed state. And I haven't thought about it much, but I would believe that a traditional method, except for quantum state reconstruction, you wouldn't get that. That's a long answer, but it's tricky, actually.
So yeah, this is, I think, it's very exciting to see you pushing this into really the many body regime and this outlook about certifying quantum simulations. I think is a very exciting prospect. So with that, I think, there are actually some more questions, but we would like to actually also give people a chance to just directly ask you their questions themselves. So particularly, if you typed a question into the chat, and we didn't ask it, I really encourage you to join the discussion with Manuel after the seminar and ask your question to him directly. So with that, let's just thank Manuel again. And I will just take a moment to advertise next week's seminar. Let me pull up a slide here. So next week, the AMO seminar will be given by Alexei Gorshkov from JQI. And Alexei will be talking about dynamics of quantum systems with long-range interactions. The European-run quantum science seminar is still on summer break, but will be returning on September 3rd. So tune back in then. And at this point, I believe that somebody placed a link to the discussion with Manuel into the chat. Fantastic. So I really encourage everybody to hop over into that other Zoom room and continue asking Manuel your questions. Let's thank him one more time for a wonderful seminar.
Thank you.